This is part 5 of the truss subsection of the structural design section of our aeronautical engineering course. In the first 4 parts we looked at trusses that looked like this. They were made of zigzags. They were on 45-degree angles with the flanges. Those are 45s. This is 90. So these are 45-degree right triangles. In the other examples we looked at, we had a 100-pound weight hanging from the center, and another one we had a 100-pound weight hanging from this point 3/4 of the way across. But in this example, we're not going to hang any weight from the truss, but we're going to say the truss itself weighs 100 pounds. And then we're going to analyze the loads in each segment of this truss. Okay, let's assume that the zigzags are made of the same material that the top flange and the bottom flange are made of. So first off, we need to figure out the length of all the segments here and figure out how many pounds per foot we have. Okay, let's say that it's a 1 foot high truss, 1 foot between the bottom flange and the top flange. Well, these are all 45-degree right triangles. So it's 1 foot from here to there, it's 1 foot from here to there, and 1 foot from here to there. So each flange segment is 2 feet, and each zigzag is 1 times the square root of 2, or 1.414 feet. So our total length is 1, 2, 3, 4, 5, 6, 7 times these 2 footers. 7 times 2 plus 1, 2, 3, 4, 5, 6, 7, 8 of these square root of 2 length zigzags. So 7 times 2 plus 8 times the square root of 2 equals a little over 25 feet. So we're talking a little less than 4 pounds per running foot. So one segment here, a flange segment, will weigh 7.9 pounds, and a zigzag will weigh 5.587 pounds. So let's look at this bottom left point right here. Okay, we know that the beam weighs 100 pounds, and it's symmetrical. So we have 50 pounds on our right bridge support, and we have 50 pounds on our left bridge support. Well, our support is pushing up 50 pounds, but is the stress in this member the same as the stress in our weightless bridge with a 100-pound weight hanging from it? That one was 70.7 pounds because 50 times square root of 2 was 70.7, but in this case we have the weight of these segments to deal with. This segment weighs 5.587 pounds, so let's say half of its weight is on this point and half of it is carried by this point. Well, this segment is a 2-footer, so it weighs 7.9 pounds. We'll say half of its weight is on this point and half of it is on this point. So let's just draw this point, which I've already done. Here it is. Okay, we have half of our 5.587 pound zigzag, which is 2.793 pounds, acting on this point. We have half of our 7.9 pound bottom flange segment, the 2-foot long segment. It weighs 3.95 pounds, half of 7.9. So 2.793 plus 3.95 gives us 6.744 pounds of weight of these 2 segments resting on this point. With the bridge supports pushing up 50 pounds, the stress in this member doesn't have to be a whole 50 pounds because part of that 50 pounds is carrying our 6.744 pounds of weight of half of these segments here, the zigzag and the flange segment. So 50 minus 6.744 pounds gives us, let's see, 50 minus 6.744 equals 43.256 pounds. Okay, so that's our vertical component. So the load that this must carry, it would be that times the square root of 2. So times 2 invert square root equals, it would be 61.17. Here we go, our resultant load is 61.173 pounds instead of 70.7 as it was in our weightless bridge. Okay, so let's look at our next point here. Let's look at this point. Okay, we've established that the load in this zigzag is 61.2 pounds of compression. It's somewhat lessened because of the weight of these members figuring into the equation. So let's look at this top point here. We have a 61.2 pound push in that direction on it. Okay, whoa, come back here. Okay, here we go, 61.2 pounds of compression at our 45-degree angle. Okay, so we have a zigzag, another zigzag, and a top flange member. We're going to say that half the weight of each of these members is pushing down on this point. So the force that this zigzag is pushing up on this point is somewhat counterbalanced by the weight of all three of these segments pushing down on this point, which means this zigzag doesn't have to pull down on this point as much as it would if this were a weightless beam. So let's do the math here. We have two zigzags that weigh 5.587 pounds each, so half of that would be 2.79 pounds. 2.79 pounds for one zigzag, 2.79 pounds for the other zigzag, and there's a 2-footer which weighs 7.9 pounds for the whole 2 feet. But we're going to count only half of it. The other half rests on another point, so 3.95 pounds. So we add these three numbers together, and let's go ahead and do it. 2.793, we'll forget the rest of the numbers, plus 2.793 plus 3.95 equals 9.536 pounds. But the vertical component of this, let's see, well, I better store that. Yeah, our vertical component was 43.256 pounds. So 43.256 minus the weight of all these, recall to get that, equals 33.72 pounds would be the vertical component that this zigzag has to balance out. So we'll multiply it times square root of 2 times 2 invert square root equals, we get 47.7. So we have 47.7 pounds of tension in this segment. What we have essentially done is we've set our 100-pound truss, we have called it a weightless truss, and we have a bunch of little weights hanging from each point of this truss. The weights hanging from each point being equal to the weights of the members connected to each point. Of course, one member is connected to 2 points, so we put half of its weight on one point and half of it on the other. So the weight of half of this zigzag plus the weight of half of that zigzag plus the weight of half of that flange segment plus the weight of half of that flange segment adds up to 13.49 pounds. The weight of half of that one, half of that one, half of that one, and half of that one is another 13.49 pounds. That's what we have for that point, that point, that point, that point, and that point. Of course, these points only have 2 zigzags and 1 flange member attached to them, so half of each of them is 9.54 pounds. And these points, there's 6.744. Remember that one? That was the first total of the weights of the segments, half the weights of the segments that we used to figure out the stress on this zigzag. So there's no point in figuring out all of these. We figured out the first 2 points, but we don't do anything new by figuring out the rest. You just use the same methods that we've used so far. All the vertical components add up to 0, all the horizontal components add up to 0, and what you'll get when you're all through are these numbers. 61.2 pounds compression on these zigzags on the end. Starts getting less, 47.7 tension on these zigzags, gets even less here towards the center, 28.6 compression. And in the very center, it's only 9.5 pounds of tension. Notice there's no weight hanging from here, but this 9.5 pounds of tension by that member added to the 9.5 pounds of tension by that member is enough to hold up half the weights of these 4 segments. Do the math if you want. The zigzags are 5.587 pounds each, so 2 halves will give us 5.587 pounds. Each flange segment is 7.9 pounds each, so half of that one plus half of that one, that's 2 halves, that's 7.9 pounds. So 7.9 plus 5.5 gives us, it'd be 12, 13.4 something. Yeah, 13.49 pounds hanging from there. And here's how it compares to our weightless beam with a 100-pound weight in the center. Notice the stresses are somewhat less here, 61.2 instead of 70.7. These stay 70.7 the whole way across, but these diminish. And now that we see how these zigzags are stressed more toward the ends of our beam that is supported on the ends, we can see that the shear stress, if we were to replace these zigzags with a web, we could see that the shear stress in the web would be greater toward the ends than it would be in the middle. It'd be like a stack of paper. If we lift on each end of a stack of paper, we can see that we have lots of shear on the ends, but no shear in the middle. And there's no shear stress in the middle of a long I-beam. See, that looked like an I-beam. There we go. Well, if we had a support under one end and a support under the other end, there'd be shear stress at the ends here, but none in the middle. We'll talk a little more about shear stress in our next lesson. That'll wrap this one up. This was part 5.